Namaskara. In this session, we will start our discussions on greedy algorithms. Greedy algorithms are designed for a class of problems called optimization problems. In an optimization problem, we will have a cost function from the solution space to the real number will be defined. Every optimization problem will have an associated cost function. It associates a cost for each solution. So, for a given input, there may be several solutions S1, S2, Sk. Each one of them will have an associated cost. C of S1, this will have an associated cost C of S2 and C of, okay. When you apply the cost function on that solution, you are going to get a real number, and therefore, for each solution there is a cost associated with this through the cost function. And we are interested in that solution which has got a minimum cost or maximum cost. Okay. So, we will have two kinds of optimization problem: minimization problem and maximization problem. In a minimization problem, we would be interested in obtaining a solution whose cost is minimum. Okay. And in the maximization problem, we would be interested in a solution whose cost is maximum. If we are interested in assessing the profit that we get through a solution, obviously we would like to get a solution or use a solution that gives us maximum profit. If it is a construction or expenditure kind of a thing, then we would like to minimize the cost. So, we have optimization problems coming in two flavors: minimization problem and maximization problem. So, how do we construct a solution? Let us say we have a maximization problem. How do I construct a solution whose cost is guaranteed to be maximum? The challenge here is not that much in building a solution. Usually constructing some solution will be somewhat easier. It is typical. However, arguing that that particular solution has got optimum cost is very challenging. Okay? That is the tricky part of it. And oftentimes our intuition may misguide us. We may think that a particular process would build an optimum solution, okay, but indeed it may not be the case. Okay. So, let us look at some examples and the flavor in which the optimization problems are presented and a kind of a greedy approach for solving those problems. Okay. The first one is a very familiar one, the shortest path problem. Let us say you are given a directed graph. We will take a very simple directed graph. It is an extremely simple directed A, B, C, D. It is a directed graph. Okay. And you are interested in finding the shortest path from A to D, shortest path from A to D. Okay. One intuitive way in which we can build the shortest path is choose the cheapest option at every stage. For example, from A you have two options. I have not assigned the weight yet, I will assign it in a while. You have several options, outgoing edges. Choose that edge which has got the least cost, and from there again choose the least edge which would leave that, and so on. In this way, by choosing a series of minimum cost edges, you hope to build a shortest path, but it is not going to work. We can see right in this example. For instance, if this is 50 and this is 75, as per our strategy we would choose 50 because we would like to keep choosing the cheaper options and then build the entire shortest path through a sequence of such cheap choices, minimum cost choices. But suppose this is 100 and this is 250. What happens after coming from A to C? You have to use CD and the total cost will be 300, whereas this will be 175. So you can see that keep choosing the minimum cost edges at every possible vertex and try to build a path from A to D. So in general you are given a graph G, it is a directed graph with vertex set V and edge set E. You are given two vertices S and T. From S to T you would like to find the shortest path. Okay. The approach I have told you is called a greedy strategy. Okay. So what we are trying to do is the following. You have a vertex S, there are several choices, but you take the one that has got the least weight or what is known as optimum choice. It is called optimum choice. In fact, this is called locally optimal choice. Locally means from S you are considering only its neighbors, only the outgoing edges, and you are taking the minimum. Okay, that is called locally optimal choice. And having come here, again there may be several choices and you take another locally optimal choice. Locally optimal means there is, you are not going to consider the whole, you are going to consider a small portion, a subpart, and that defines the locality. That is why it is called local. It is an optimum choice because among several edges you are choosing the edge that has got the minimum weight. So at every stage in this way you are going to make a locally optimal choice. Okay, you are going to take the locally optimal choice and let us say you reach T, from S to T. So this kind of a series of locally optimal choices, in this example a series of minimum cost edges okay, a series of minimum cost edges, okay, hope to form a shortest path. So, a series of locally optimum choices hope to lead a globally optimum solution. So, you are going to make a series of locally optimal choices. So, you will make a series of locally optimal choices and then construct a solution, and you expect that to form a globally optimal solution. This is the idea behind the greedy algorithm. So, the greedy algorithm is attempting to build an optimum solution by making a series of locally optimal choices. So, what we mean by local is it depends on the context and it depends on the problem. Okay? So, a smaller portion of the input or a smaller sub problem would be examined, and for that context, okay, a locally optimum solution is built. Here you have several edges, you have to leave yes. What is a common sense? Choose the edge that has got the minimum cost. This is called locally optimal choice. Okay. But this need not, this is a strategy, but this strategy may or may not work. We have seen an example where it does not work. Let us look at another example where it is not going to work. Okay. So, this is called coin change problem. So, you have a country, assume that the country has issued coins of various denominations, D1 greater than D2 greater than D3, dk equal to 1, let us say 1 unit. So, it has got k coins, these are all the denominations, the values of these coins. For example, we have let us say 2 rupee coin means 200 paise coin, 100 paise coin, 50 paise coin, 25, probably 10, 5, 1. These are all various denominations in which you have coins. Okay. And you have a value m is to be paid, or you have to, let us say, receive a value m. Okay. For instance, you have used a vending machine, you have paid some money and you got a merchandise, and the balance is to be paid by the vending machine back to you. Okay. So, some value m is to be paid back to you. You do not want to have a large number of coins, okay. That will make your wallet or your pocket very heavy and uncomfortable. You would like to have that value m be paid with minimum number of coins. M is a value, a target value, be paid with minimum number of coins. The goal is any m you want to pay back. You have several solutions, each solution will use certain number of coins, all right. So, let us take for example just to 50, 20 and 1, 50, 20 and 1. Assume that you have a country where only 3 denominations are available, 50, 20 and 1. How will you pay 140? Now you go greedily. So, you try to use as many high denomination coin as possible, as many high denomination coin as possible. The hope is that with small number of coins you are accounting for big values. For instance, I can use 50, I can use 2 50 paise coins and thereby account for 100 paise with 2 coins, right, because I am trying to minimize the number of coins. With 2 coins I can account for 100. Now for the remaining 40 I again use 2 and I am done. So I have a 4 coin solution. Of course, I have several other solutions. I can use 7 20 paise coins, that will also pay 140, but it is using 7 coins. I can use theoretically 140 1 paise coin, that also pays the money back, except that you have 140 coins. It's a bad solution, alright. But what I am interested in is paying you back 140 with minimum number of coins. Is 4 a minimum number? Do you have a solution with the 3 coins? With the 3 coins, right, it cannot have 1, none of the coin. If there is 1 coin with 1, with the other 2 you have to make 139. There is no way any 2 coin here will make 139. Therefore, it cannot contain 1. Okay. So, if it contains 20, another 120 you have to make up with the 2 coins. There is no way you can make 120 with the 2 coins, because one of the coins, if it is 20 out of 3, right, the other 2 should make up another 120. That is not possible. There is no 3 coin based solution. There is a 4 coin solution, therefore 4 is optimal. I have demonstrated a 4 coin solution. I have given an argument that 4 is also optimal. Okay, it is a minimum number of coins. So you are able to get the minimum number. However, this is not going to get for all value if you use this strategy. So what is the strategy? The strategy is use as many higher denomination coins as possible. You want to minimize. So with small number of coins you want to account for huge amount of values. Therefore the natural strategy is use as many higher denomination coins, and that is what I did for 140. For 140 I can use 2 50 paise coin. Well, with this I am accounting for 100, and 2 20 paise coins, with that account for 40. 140 is accounted by 4 coins. But this strategy fails for 65. Let us use as many high denomination coin as possible. For 65 I can use only one 50 paise coin, that accounts for 50. Remaining 15 I cannot use 20, there is no way I can use 20. So I have to skip that. So (15 into 1) 15. 65 is done with the help of 16 coins. I have a solution, and the solution based on my greedy strategy. This is the called greedy strategy. You are greedy about reducing the number of coins. So you are trying to use as many high valued coins as possible. Use as many high valued coin as possible. That is going to give locally optimal choice. So you are going to make series of decisions. How many 50 paise coin, how many 20 paise coins, how many 1 paise coin. So you have done a series of locally optimal choices, and that has given you a solution. This is not optimal, okay, because 65 can be paid like this. 3 20 paise coins will give you 60, 5 1 paise coin will give 5. So with 8 coins I can pay 65. You do not need 16 coins, it is enough if you use 8 coins. Okay. That shows that greedy is not optimal, there are better solutions. And what are we optimizing? Number of coins. The number of coins that we optimize. So the important point is, we may have a greedy strategy, but that strategy may or may not work. That is actually the reason why every greedy algorithm requires a formal proof of correctness, because your intuition may be wrong. Okay, so let us consider another example. We will now get to consider the following problem. Okay, these are called knapsack problem. Okay. So there is a knapsack, just a bag, that is it. Okay. You have a capacity constraint. For instance, if you have to travel abroad or air travel, there is a limitation on the number of kilograms, the amount you can carry with you. Okay. Typically you say 20 kilograms. Okay. This is a limit, this is a capacity constraint. You can take only 20 kilograms. If you take anything more, you may have to pay heavily. So you would like to take only, you are allowed to take only 20 kilograms. But then there are several things you want to take. So you have several objects, O1, O2, etc., On. There are n objects. Each object has got certain weight and it has got certain importance to you. It is very essential for you, okay, because it gives you some benefit. It is very essential, right. You feel that I need. This is modeled in the following way. Each object has got a weight and it has got a profit value. It has got a profit value. It has certain level of importance that is modeled by P and it consumes certain weight that is given by W. And W2 P2 and Wn Pn. All these W2 Wn P1 to Pn are for a 1 unit of that object. For 1 unit of object, it weighs W1 and it gives a profit P1. And 1 is your ideal limit, okay, whatever you would like to take, that is defined as 1 unit. For example, for your trip, for a travel, you would like to take 10 shirts, okay, and after taking whatever you want you find that it is exceeding the limit, so you have to cut down. Okay. You may now compromise, all right, I do not want 10 shirts, I will take only 6, all right. So, what you have done is you have taken a fraction of that. Ideally your 1 unit is 10 shirts, but you have taken only 6 shirts, that is 0.6. This is what you have taken. Say let us say object 1 is a shirt. 1 unit weighs W1 means 10 shirts, they weigh certain things. But you are taking only 6, so you are taking only 0.6. This is x1. x1 is the fraction of the object that you have chosen. x1 is the fraction of the object that you have chosen. x2 similarly is the fraction of object 2. In this way, with respect to each object, a fraction is associated with, because we are assuming that we are normalized and it is unit weight and unit profit for 1 unit of that object. But you are not, ideally that is what you want to take, 1 unit is what you want to take, but you will not be able to take all that. Ideally you may want to have 2 kilograms of let us say a dal powder, but finally you say that is too heavy and then you take only half a kilo. Ideally 2 and 2 to half is 1/4, 0.25. Okay. So, in this way you are going to have fractions. So, x1, x2, x are fractions, 0 less than or equal to xi less than or equal to 1. Why you are taking only a fraction of a particular object? You cannot take in full. If you keep taking in full, it will exceed the limit. So, this should satisfy what is known as the weight constraint. Sigma xi wi is less than or equal to m. You are taking, let us say O1, On, this is weight 1 unit weight Wn. You have taken x1 of this, x2 of this, xn of this. So, sigma xi vi will give you the total weight of the objects you have picked up, that should be less than or equal to m. This is called the capacity constraint. But for 1 unit of object when you take, you get a profit of Pi. So when you take Xi, you are going to get a profit of Xi Pi. This is profit of Xi Pi. The profit earned by your choices, okay, is Px. Obviously, you would like to maximize the profit. You have to find out x1, x2, etc., xn, so that find x1, x2, etc., xn, so that Px, which is sigma xi Pi, is maximum. This is maximum. So let us give the picture O1, O2, On, and there is a capacity constraint M. This has the weight W1, W2, etc., Wn, and it gives the profit P1, P2, etc., Pn. You have to take x1 fraction of this, x2 fraction of this, xn fraction of this. These xi's are fractions, 0 less than or equal to xi less than or equal to 1. Choose xi's so that you have sigma xi wi is less than or equal to m, and sigma xi pi is maximized. So here is an optimization problem. In this optimization problem, you have to maximize the profit. Okay. So one thing which you can do is choose the one that gives you maximum profit as much as you can. Okay, as much as you can, you take it. So for example, I have 3 objects O1, O2, O3. I have the profit 24, weight 18, okay, and profit 18, weight 12, profit 16, weight 10. Capacity M is 20. Capacity M is 20. Let us take as much as possible high profit yielding one. Here the high profit is for O1. O1 gives you 24. Take that as much as possible with the hope that when you take large amount of that object, you get more profit. So take that as much as possible. The maximum is 1 because 0 less than or equal to xi. Our ideal limit is called 1 unit, and whatever you are taking actually is a fraction of that. So let us assume that you are able to take the maximum. The maximum can be 1. So when I take O1 1 unit, this is x1. How much profit I earned? 24. So 1 into 24 This is the profit, 24. And it is weighing 18. So, out of 20, this is using 18. The total is 20, out of which your first object is using 18. You are left with only a capacity of 2. Out of 20, 18 is used up. Let us take this as much as possible. Let us take that as much as possible. So, I can take 2 by 12 of it, right. It is a fraction. I can take 2 by 12. So, x2 is 2 by 12. When x2 is 2 by 12, so you are going to take 2 by 12 of object 2, and when you take 2 by 12 of object 2, 2 times 18, 3. This much profit you get, 2 by 12 of them. So, this will be 2 and 3. It is 3. Okay. The total profit you are going to get is 3. So, x2 equals 2 by 12, and this is giving me a profit of 24, this is giving me a profit of 3, and this is occupying 18, and this is occupying 2. So, your bag's capacity is fully utilized. 20 is the limit, already I have 20. So, x3 is 0. I cannot take any of this third object. My limit has already been reached. Therefore, nothing, you do not get anything. So, the profit you are getting is going to be first 24, then 3, and totally 27. A profit of 27 you have got. So, let us O1, O2, O3, 24, 18, 18, 12, 16, 10. I have taken x1 to be 1, x2 to be 2 by 12, x3 to be 0. In this case, sigma xi wi is 1, xi is 1 weight, this is profit, this is weight. 1 times 18 is 18, 2 by 12 times is 2 plus 0, that is equal to 20. What about sigma xi pi? Xi pi is the profit for 1 is 24, the profit for this 2 by 12 of 18 is 3, the profit is nothing. So, this is 27. Okay. So, you earn a profit of 27 by this greedy approach. Is this optimal? In general, this will not be the case. For example, consider simply the following fraction: x1 equal to half, x2 equal to half, x3 equal to half. Okay? Consider just this one. So, when x1 equal to half, the weight for this will be 9. When x2 equal to half, the weight for this will be 6. When x3 is half, the weight for this will be 5. So, altogether 20. So, if you take half, half, half of each object, you will fill the knapsack to its capacity fully utilized. But what about the profit you are going to get? Half of 12 will be, half of 24 is 12, half of 18 is 9, half of 16 is 8, and you are getting a profit of 29. This is very interesting. This first of all shows that this is not optimal. I have another solution which gives a better half, half and half. That gives me a better profit. This problem is known as fractional knapsack problem. This is called fractional knapsack problem. Okay. So, we will take a closer look at this and a greedy strategy for solving this in our next session. Thank you.